Let's start with the reasons why the 3C system became a necessity in today's cars. Essentially, the development of the 3C system is a response on the part of automakers to meet today's tighter emission control standards. Standards that have become so demanding over the years that onboard computers offer the only effective way of dealing with them. But more of this later. First, it's important to understand how we got to this point. It began in 1968. That was the year automakers were first bound by law to control exhaust emissions. Initially, the requirements were met by PCV valves, pollution canisters, and exhaust gas recirculation systems. A few years later, the catalytic converter was developed. It used a catalyst of platinum and palladium to add oxygen to the exhaust gas and produce harmless carbon dioxide and water. By 1979, the catalytic converter had helped to reduce the levels of pollutants considerably, with one notable exception: oxides of nitrogen. The inability of the catalytic converter to handle oxides of nitrogen was a serious cause for concern, because when oxides of nitrogen mixed with the hydrocarbons in the exhaust, it produced that well-known modern problem called smog. By 1981, oxides of nitrogen levels were becoming critical. The government responded by cutting the carbon dioxide and oxides of nitrogen emission standards in half, while keeping the hydrocarbon standards the same. In order to comply with these tougher measures, automakers introduced the dual bed converter. Unlike the early converters, which did little to reduce oxides of nitrogen, the dual bed converter added the reducing catalyst rhodium to the system. Rhodium took the oxygen out of the oxides of nitrogen, turning it into pure nitrogen, the stuff that makes up 78% of the air we breathe every day. At first, the dual bed converter seemed like the ideal solution to the oxides of nitrogen problem, but it turned out to be more than any car could handle, requiring more precise control of fuel and timing. The logical solution was the speed and accuracy of the computer. Engineers determined that the catalytic converter was 90% efficient when engines were running at an air-fuel ratio of 14.7 to 1. Although this was the magic formula for emission control and fuel economy, there was one small problem. Cars didn't work that way. A constant 14.7 to 1 ratio will give you problems ranging from hard starting to insufficient power to pass or climb hills. The real-world solution was to keep the air-fuel ratio as close to 14.7 to 1 as possible, while being able to compensate for other driving needs like starting, passing, even high altitudes. That's where the 3C system comes in. It evaluates engine needs and provides optimum control over air-fuel ratios and timing to assure the best emissions management and fuel economy. In this presentation, the 3C system we'll be examining is GM's Electronic Control Module, ECM for short. This high-tech wonder is capable of making over 250,000 computations per second, and is so advanced that while you're waiting for the light to change, your ECM is monitoring each of its inputs, usually a dozen or more, 10 times every second. ECMs are located on the right-hand kick panel of most rear-wheel drive cars and behind the glove box on most front-wheel drive cars. All they need to run on is a dependable supply of electricity, a little when the car isn't running to retain their memory, and a few volts during operation. ECMs are dependable too, and there are only 3 ways you can damage them. One is to reverse battery polarity. Another is to get them overly wet, as can sometimes happen when you drive through a flooded area. The third is induced voltage, often referred to as voltage spikes. You'll find ECMs come in a few different models. There are 1, 2, and 3 board versions, a designation based on what they're expected to do. For our purposes, we'll be concentrating on the basic 2-board ECM. The function of the 2-board ECMs depends on what is called a programmable read-only memory, PROM for short. Essentially, the PROM is a library of information about the car in which it is installed, storing dozens of pieces of important data, including engine specs, gear ratios, tire sizes, and carb types. In short, the PROM provides the computer with a plan, a blueprint for keeping the vehicle running the way the manufacturer intended and the government requires. As a result, the PROM knows what to do under all conditions and operates in what are commonly referred to as modes. These modes are the shutdown mode. This means below 200 RPM and 9 volts of battery power, the computer shuts down completely. However, the car will continue to operate. The second mode is the startup mode. The computer orders the carburetor to run full rich for a period of time determined by the coolant temperature. This results in anywhere from a 1 to 2 second to a 70-second delay. When the startup mode timer and the ECM are satisfied, the ECM switches to open loop operation. Fuel control is now based on both engine temperature and engine vacuum. In open loop, the air-fuel mixture is controlled for best efficiency until full operating potential is achieved. The ECM will switch to closed-loop operation when coolant temperature is between 140 and 160 degrees and the oxygen sensor is above 600 degrees. This is the ideal running condition for the vehicle. It is only in closed loop that the engine functions at peak emissions control and fuel efficiency. In closed-loop operation, fuel mixtures control is determined from data received by the oxygen sensor. It is only in closed loop that the computer delivers a consistent 14.7 to 1 air-fuel ratio. The last mode of operation is called power enrichment, or sometimes WOT, wide open throttle. The computer will shift to this mode in conditions requiring quick acceleration. When the throttle is open to greater than 86%, the ECM sends a constant enrichment command to the mixture control solenoid. Of the 5 modes we have discussed, open and closed loop are the most significant. Open loop gets us where the engine needs to be to achieve closed loop operation. Then closed loop takes over, delivering all the efficiency the engine was designed to provide. It's important to remember that fuel mixture is controlled by coolant temperature and vacuum sensors in open loop, and by the oxygen sensor in closed loop. Also, only in closed loop can the ECM maintain the 14.7 to 1 air-fuel ratio. Now that you understand the 5 types of modes, the next step is to see how the ECM determines which mode to be in. This is accomplished through input sensors that relay information to the ECM. Once the ECM has the proper data, it evaluates it and picks the proper mode of operation. The number of input sensors will vary by type of vehicle and special equipment. Regardless of the number and type of inputs, the ECM uses this data to direct its outputs to do one thing: make the vehicle run more efficiently. Let's quickly review the major input sensors and their role in the overall operation of the ECM and engine. In later tapes, we'll provide a detailed explanation of each individual sensor and its operation. Probably the most important of the input sensors is the coolant temperature sensor. It provides the ECM with information to function in open-loop operation and regulate exhaust gas recirculation, EGR, early fuel evaporation, EFE, evaporative controls, air pump operation, and idle speed. This, combined with the vacuum or MAP sensor, makes open-loop operation possible. The vacuum or MAP sensor not only provides data on the converter clutch operation and load on the engine, but also helps determine the fuel mixture necessary to get the engine to closed-loop operation. The next important sensor is the oxygen sensor. This input provides the ultimate necessary data to establish the 14.7 to 1 air-fuel ratio in closed loop. Without the oxygen sensor, there is no closed loop. The other input sensors are as follows: the barometric absolute pressure sensor, BARO for short, which reads atmospheric pressure and altitudes to control timing. The throttle position sensor, which determines the angle of the throttle and its rate of movement, allowing the ECM to make adjustments in timing, fuel ratio, and converter clutch operation. The RPM sensor that provides data necessary to proper timing and idle speed adjustment. A vehicle speed sensor, which tells the ECM how fast the car is going and helps control converter clutch. Electronic speed control or cruise control, and in some cars, idle air control. A brake switch sensor that talks to the ECM about converter clutch control. The park neutral sensor relates to idle speed, timing control, and converter clutch. And last but most important, the ECM has 2 power inputs. One provides a constant power supply to maintain ECM memory retention, and the other maintains full power after ignition on to operate the ECM functions. Keep in mind, not all vehicles have all the same input sensors. There are minimum function, full function, and Oldsmobile LC function ECM units. Whatever the type of ECM, however, they all work the same basic way. input in, control commands out. Once the ECM has collected data from all these various inputs, it evaluates and uses it to give commands to as many as a dozen outputs. Output controls energized by the ECM provide peak operation of the various systems. These systems include the carburetor, which controls air-fuel ratio, air management, spark timing, idle speed on some cars, evaporative emission control, EFE and EGR functions, and converter clutch operation. The ECM is able to do all these things based on a system of input voltages provided by the sensors. Because it operates on input voltages, the ECM has what is known as a digital system. Stored in the PROM, programmable read-only memory, are specific voltage parameters for that vehicle. Any deviation from allowable voltage ranges will result in a check engine signal flashing on the instrument panel. While there are only about 8 or 9 basic ECMs, they can function in a great number of different vehicles by the use of the correct PROM. Each PROM has an identification number which must match the vehicle in which it is installed to function properly. A great service tip is to be sure the numbers match before you pick up the first tool. We'll talk more about that later when we get into the specifics of ECM and service. In addition, the ECM has a limited diagnostic capability. When certain parts of the system are not functioning to specifications, the computer will store a diagnostic code number. The number will remain in the computer memory even if it was merely a temporary problem like a loose wire. The trained service technician can read these trouble codes and know the nature of the problem stored. This trouble code will stay in the computer memory until battery voltage is removed from ECM or the car is started 50 times. You'll find more about trouble codes and their value in later tapes. This concludes the overall theory and function of the 3C system. Equipped with this basic understanding, you should now be able to view computer-controlled problems with a high degree of confidence. In fact, with its self-diagnostic capability, it has already done some of the work for you before it even drives in the door. In our next tape, we're going to get under the hood and see exactly where these inputs and controls are located and how they work.